years I'm free. It's time to conquer Earth.
Alpha, Rita has escaped. Recruit a team of students with attitude.
Go, go, Power Rangers! Go, go, Power Rangers! Go, go, Power Rangers! You mighty morphin Power Rangers!
Since Rita escaped, she's been destroying buildings and harming civilians in her attempt to conquer Earth. Luckily, the MDP Rangers have built the ultimate robot to rescue people quickly and efficiently.
For pathfinding, we primarily use A-star search, with an added turn cost to minimize turns and a penalty cost to prevent the robot from coming too close to obstacles. Each obstacle has 4 possible endpoints, which helps account for specific edge cases.
We also use Dublin's algorithm, considering 6 possible paths from start to endpoint. For collision detection, we iterate through every calculated path and check if any point lies within each obstacle's assigned safety radius. The shortest possible one is selected. Both these algos are run simultaneously between every possible endpoint to create path cost tables.
We then apply a dynamic TSP solver to give us 2 optimal Hamiltonian paths. Both paths are compared and the shortest one is selected for use.
To build a vehicle fit for the MDP-19 Rangers, several powerful components are used. To start, 2 DC motors are used to power our vehicle and a servo motor to steer our vehicle in the right direction. Our vehicle is also built with an STM microcontroller, which contains the gyroscope unit to determine the turning angle, and utilizing the PID controller to help our vehicle move in a straight line by calibrating the spin of our tires according to the reading from the gyroscope. This allows the vehicle to move quickly and make accurate turns to navigate around the buildings. To ensure our Rangers' safety, we also installed an ultrasonic unit and IR units, which feedbacks the front-facing and side-facing distance to our vehicle and prevents the vehicle from crashing into any building or obstacles.
Image rank!
Next, MDP-19 Rangers will also need help to identify our victims. To assist them, the image recognition team innovated and trained the YOLO V5 model over 100,000 images and further fine-tuned it with 7,000 images. This allowed our model to accurately detect the images to approximately 99.4% accuracy. Finally, a state-of-the-art camera is installed in the vehicle to capture images for our model to detect.
Android!
Ensuring that Rangers are able to easily control their vehicle is vital in their ability to save the world. This is where the Android app comes in. Once the robot is connected via a Bluetooth connection, Rangers are greeted with the main UI. The 2D arena grid displayed allows for easy placement of obstacles with a simple drag and drop gesture. The X and Y position of the obstacle is highlighted in the axes, making it fast and reliable. A simple tap allows Rangers to select the direction of the image on each obstacle. Removal of obstacles is equally simple.
Once the obstacles are placed, Rangers can then start tasks, which places the robot on the grid and starts a timer. Position of the robot and the obstacle ID will be updated on the grid in real time. The timer stops automatically after the task is complete. Any status messages sent back by the robot are displayed on the status bar with a timestamp assigned. Rangers can scroll through them using the buttons or swipe gestures. Finally, there is also a chat tab on the app, allowing Rangers to directly chat with the robot.
Last but not least, we need a brain to synchronize the hardware in our high-tech vehicles. This is done by installing a sophisticated Raspberry Pi 4 equipped with multi-threading, which allows simultaneous task coordination between the STM, Android, algorithms, and image recognition. To start, obstacles location placed on the Android are sent to the RPi, after which a HTTP request is made to the Flash server, which returns the path and its respective commands. After the start command is issued by the Android, the path and respective commands are sent to the STM and Android simultaneously. When there is a snap command, RPi will take a photo and forward it to the image recognition server that's a HTTP request. Result of the detected image ID will be sent back to the Android. This process repeats until all commands are processed by the STM.
For task 2, we made use of the ultrasonic and infrared sensors to maneuver around the obstacles.
Before entering the car park, we first take a snapshot of the car park in order to determine the relative orientation of the vehicle. We then angle the vehicle to be aligned with the car park before driving straight in.